Hello everyone, this is Solved by Hand channel. Welcome to the channel. Today we will solve problem in heat and mass transfer. So today we'll solve problem in heat and mass transfer. The title of this problem is heating of a copper ball. So we'll solve problem called heating of copper ball. So let's go. So this is the statement of the problem. So heating of a copper ball. A 10 centimeter diameter copper ball is to be heated from 100 degrees Celsius to an average temperature of 150 degrees Celsius in 30 minutes. Taking the average density and specific heat of copper in this temperature range to be this is the density is 8,950 kilogram per meter per cubic meters, and Cp, which is specific heat at constant pressure, is equal to 0.395 kilojoule per kilogram per degree Celsius. So the questions are this. So we have three questions. So question E, the total amount of heat transfer to the copper ball. So we have to determine. The total amount of heat transfer to the copper ball. Question B, we have to determine the average rate of heat transfer to the ball. Question C, we have to determine the average heat flux. So this is the figure of the problem. So we have a copper ball, and it is at the temperature of T1 100 degrees Celsius, and we have to heat this copper ball to the temperature T2, which is equal to 150 degrees Celsius. It is a copper ball, so this is the formula for the area of the copper ball, and this is the heat added. So I will read the problem again. I will read the statement of the problem again. A 10 centimeter diameter copper ball is to be heated from 100 degrees Celsius to an average temperature of 150 degrees Celsius in 30 minutes. So we have to heat this copper ball from the temperature of 100 degrees Celsius to 150 degrees Celsius. At the time of heating is 30 minutes. We have to heat it during 30 minutes. Taking the average density and the specific heat of copper in this temperature range to be this is the density. So this is the average density of the copper ball. So 8,950 kilogram per cubic meter, and the Cp, which is specific heat. The specific heat of the copper ball is 0.395 kilojoule per kilogram per degree Celsius, respectively determined. So we have to determine A. So we have to determine the total amount of heat transfer to the copper ball. B, we have to determine the average rate of heat transfer to the ball, and C, we have to determine the average heat flux. This is the figure of the problem. So we have to bring the temperature of the copper ball from 100 degrees Celsius to the temperature T2, which is equal to 150 degrees Celsius. We have to do that in 30 minutes. So we have to do that in 30 minutes. So it is a copper ball. It is made of copper. It has a density of 8,950 kilogram per cubic meter, and it has a specific heat of 0.395 kilojoule per kilogram per Celsius. This is the formula for the calculation of the area of sphere, because the copper ball has the shape of sphere, and this is the heat added. So without any further delay, let's go to our paper in order to solve our problem. So let's go to our paper. So I will go here. I will go screen, show taskbar, and I will go to our paper. So this is our paper. Let's start solving our problem. So this is a problem of heat transfer. So the first thing that we have to write is to write the assumption. So writing the assumptions. Assumptions. So we can use constant properties can be used can be used for copper at the average temperature. So since copper is solid, so we can use constant properties can be used for the copper at average temperatures, at the average temperature. So this one, average temperature. So let's continue. Let's write properties that we have. So properties, the properties that we have to use for the copper ball are these properties. So average density of copper rho is equal to, so rho is equal to 8,950 kilogram per cubic meter. So those the average temperature. So and also for specific heat, specific heat of copper. So copper is a solid. So So for the specific heat, so Cp, specific heat as constant pressure, it is equal Cv. It is equal to specific heat at constant volume. It is equal to C. So because here we are talking about solid, so copper is solid, and I will take one value. So specific heat at constant pressure, it is equal to specific heat at constant volume. Since we are speaking about solid, so we can speak about C. So we don't speak about Cp or Cv. So this will give us the value of 0.395 kilojoule per kilogram per degree Celsius. So those are the values. So those are the properties that we have to use in our problem. So those are the properties that we have to use in our problem. So the first thing that we have to determine, what is the first thing that we have to determine? Let's go back to our problem. A, we have to determine the total amount of heat transfer to the copper ball. So A, we have to determine the total amount of heat transfer to the copper ball. So we have to determine this Q. So we have to determine this Q. The total amount of heat transfer to the copper ball. We have to calculate this. The total amount of heat transfer to the copper ball. Let's go to our paper. Screen, show taskbar, and let's go to our paper. So question A. Question A. Question A that we have to solve: the amount of heat transferred to the copper ball, and we will have to give to this heat transferred. I will give to this heat transferred we'll give it the symbol Q. So we have to calculate Q. So let's first, so in order to calculate this Q, so the energy transfer to the system, we have, our system is the copper ball. Energy transfer to the system is equal to energy increase of the system. Energy increase of the system. So what is the energy transfer to the system? So what is the energy transfer? So energy transfer to the system is Q is equal to energy increase of the system. So energy increase of the system is delta U. So delta U, and delta U for a copper ball is equal to M, the mass of the copper ball, times C, which is here. So C that we'll use here. C, maybe we'll call it C average. C average. So equal to C average. So average specificate C average times T2 times T1, and we have T2 is equal to 150 degrees Celsius and T1 is equal 100 degrees Celsius. So because here, as we have seen, so the temperature will be increased from 100 degrees Celsius to 150 degrees Celsius. So T1 is 100 degrees Celsius and T2 is equal 150 degrees Celsius. So let's go back to our paper. Let's continue. First of all, we have to calculate the mass of the valve. So since we need here, so we need here the mass. So we need to calculate the mass here. So we need the mass. So we have to calculate first the mass. Let's calculate the mass of the ball. Calculation of the mass of the copper ball. So calculation of the mass. So the mass is equal to the density times V, which is the volume of the ball, is equal to the density times the formula. What is the formula for the calculation of the volume of sphere? The formula says is 4/3 times pi times the radius to the power 3. So to the power 3 is equal to density times, here still talking about the volume, which is 4/3 pi, and what is the radius? Radius is d/2. Everything is to the power 3. Let's continue. Is equal density times 4/3 pi. This will give me d/2 to the power 3 will give me d to the power 3 over 8, and this will give me the density times, this will become, so here we have 8 is 4 times 2, so this 4 will be cancelled with this 4, and at the end I will have the mass is equal to the density times pi times d to the power 3, which is the diameter of the ball, over c. And this will give me the value of, I will calculate this. So what is the density? The density is this one. This is the density that I have to use. So the value of the density is 8,950 kilogram per cubic meter. So this is the density. So this will give me the value of 8,950 kilogram over cubic meters times pi times here the diameter. So what is the value of the diameter? So the diameter, what is the value of the diameter of the ball? So a 10 centimeter diameter. So the diameter of the copper ball is 10 centimeter, which 10 centimeter diameter, which is equal to 0.1 meter. So a 10 centimeter diameter, which means that the diameter of the ball is 10 centimeter, which is equal to 0.1 meter. So I will go back again to my paper. So I will replace the value of the diameter pi. So I wrote, so this is the density. The value of the density is 8,950 kilogram per cubic meter times pi. I wrote pi times d to the power 3. So d, which is the diameter, which is 0.1 meter to the power 3 over 6. So over 6. So this one 6. So after calculation, this will give me. So after calculation, this will give me that m is equal the mass that we are calculating. M is equal 4.686 kilogram. So this is the mass. So and for the units, we have this m to the power 3 is cancelled with this m to the power 3, and at the end we have, for the units, we have kilogram. So this is the units. So at the end we have this unit, kilogram. Let's continue. So we have calculated the mass of the ball. Why we calculate the mass? Because we need this in this value, in this formula. So we need this formula. We need the mass. Also we need C average, which is specific heat of the copper. We have already C. And we have to use the temperature T2 and T1. T2 is equal to 150 degrees Celsius, and T1 is equal to 100 degrees Celsius. So at the end, this will give me for the heat, Q is equal to delta U, and it is equal to M times C average times T2 minus T1. So if I replace every time by its value, it will give me M, which is, so the value of M is 4.868 kilogram times C average, which is 0.395 kilojoule per kilogram degree Celsius, times T2, which is equal to 130, T2 150, minus T1, 100. The value of T1 is 100, and the unit that I will use here is degree Celsius. So the degree Celsius. This will give me, for the value of Q, it will give me 92. So 92.6 kilojoule. So why kilojoule for the units? So we have this kilogram is cancelled with this kilogram, degree Celsius is cancelled with degree Celsius, and at the end for the units we have the unit of kilojoule. So this is what we have here. So, and for Q we have this value, Q is equal to this one. So let's continue. So we have, so because questions we have calculate the amount. So question A was the amount of heat transferred to the copper ball. So this was question A. Question A, the amount of heat transferred to the copper ball, Q. So we have calculated Q. So we found that Q is equal to 92.6 kilojoule. So let's continue with our problem. Question B. What is question B? I will go back again to the statement of our problem. So question B, so we have to determine in question B, we have to determine the average rate of the transfer to the ball. So in question B, we have to determine the average rate of heat transfer to the ball. So we have to calculate Q dot, that is the average rate of heat transfer. So here in question E we have calculated Q. In question B we have to calculate Q dot, which is the average rate of heat transfer to the ball. The average rate of heat transfer to the ball, which is Q dot. Let's continue. Let's go back again to our let's go back again. I have to go back to the camera. I don't know where is the camera. I have to go to the camera. Yes. And I am back again with the camera. I will go here and slideshow from current slide. Sorry. Now we are back. So I'll go back again to the camera. So this question 2. So question A is done. So we have calculated the total amount of heat transfer to the copper ball. So question A, we have calculated. I will pick the razor pointer. So question A, we have calculated the total amount of heat transfer to the copper. We have calculated the total amount of heat transfer to the copper ball. We have calculated Q. So in question B, we have to calculate the average rate of heat transfer to the ball. So in question B, we have to calculate the average rate of heat transfer to the ball. So question B, we have to calculate the average rate of heat transfer to the ball, which is Q dot. So in question B, we have to calculate Q dot. So I will go back again to our paper. So let's start with question B. So question B. So this is question B. Question B. We have to calculate the average rate of heat transfer transfer to the ball so the ball that we can call the average heat transfer to the ball that we can call Q dot average. So we have to calculate the average rate of heat transfer to the ball that we call Q dot average. So we have to calculate Q dot average. So how we will calculate this? We have to use the formula for calculating Q dot or the average rate is Q dot average is equal to Q divided by delta T and is equal. So what is the value of Q? We have already calculated Q, so we have already calculated the value of Q. I will use this Q that I have found. So Q is equal 92.6 kilojoule, and the time, what is the value of the delta T? The time is 30 minutes, and I have to do unit conversion here. I will use the fraction, so the unit conversion fraction, so I will use this fraction. So 1 minute is equal to 60 seconds, this one it will give me, so for the unit here, so this minutes will be cancelled with this one, and at the end I will have, for the units I will have kilojoule over second. So this is the unit that I will have. So this will give me the value of 0.0514 kilojoule over second. Which is what? Which is kilojoule over a second, which is kilowatt. Is equal to 0.04514 kilowatts, and I will write the final result. I will write the final result in watts. So Q average, which is the average rate of heat transfer. So the average rate of heat transfer, Q average dot, is equal to 51 times 51.4 watt. So this is the average rate of heat transfer. So I have calculated the average rate of heat transfer. So this is for question B. Let's go again to question C. So what is question C? Let's go back again to the statement of our problem. So question C. So in question C we have to determine the average heat flux. So we have to calculate the average heat flux. So we have to determine the average heat flux, which is small q dot. So for the average rate of heat transfer we use big Q dots, but for the calculation of the average heat flux, so for the calculation of average heat flux we use small q dot. So we have to calculate here the average heat flux, the average heat flux, which is small q dot, the average heat flux. So we'll go back again to our paper. I will go back to the paper. I will calculate the average heat flux. So C, which is the average heat flux, and we will give this symbol of small q dot average. So the heat flux, and the formula for calculating the heat flux is this one. So the heat flux, small q dot average, is equal to big Q. It is equal to the average heat of the average rate of heat transfer. So it is equal to big Q, which is the average rate of heat transfer. It is equal to big Q average divided by A, which is the area of the ball, which is the area of the sphere. So the area, which is the area of the ball, which is the area of the sphere, which is equal to Q dot average equal to the area of the sphere, or the area of the ball. So the area of the ball is equal to the area of sphere. So what is the area? So here we already have the formula for the area. So for the area of the sphere, or the area of the ball, which is equal to the area of sphere, is equal to this formula. Area is equal to P times D squared. So this is the area of the ball. It is equal to P times D squared. I will go back again to the calculation. Taskbar, and I will go again to the paper. So this one will give me, so I will use P times D squared, and this one will give me, so for the Q average we have already calculated, so we have already calculated Q average. It is equal to 51 times 51.4 watt, and we have to use here pi times D squared, which is D, the diameter is 0.1 meter, so 0.1 meter squared, and this will give me, so this will give the value of, for the average head flux, it will give me this value, Q dot average is equal, so after calculation it will give me 1636, and the unit will be watts over meter squared. So watt over meter squared. So the unit for the average heat flux is watts over meter squared. So this is the final results. So this is the final results. And this finishes the problem that we have solved. So this finishes our problem. We have calculated so for this problem we have calculated the amount of heat transferred to the copper ball. We have calculated it. So we have calculated the amount of heat transferred to the copper ball, Q, and we have calculated the average rate of heat transfer to the ball, Q dot average. So we have calculated the average rate of heat transfer to the ball, which is Q dot average, and we have also calculated the average heat flux, which is small q dot average. So we have calculated also the average heat flux, which is small q dot average. This finishes this exercise. I hope that we have understood everything, and I hope that we have enjoyed this problem. I wish that you continue with the channel and you see the other common videos. Thank you very much for your attention. See you next time. Bye bye.